presented by Group 7. Your presenters today are Brianna Calley, Samuel Coons, and Jaron Rochester. Today we are going to demonstrate a possible implementation of a truth table for an automotive signal light control circuit using AND, OR, and NOT gates, or using a read-only memory, ROM. Such a circuit would have controlled the signal lights of many cars, such as the pictured 1969 Mustang Shelby GT 500. Here is the truth table for this control circuit. We will demonstrate the simplification of the Boolean equation for the left back signal light, highlighted in yellow. Highlighted in green are the various input combinations that will cause the left backlight to operate. Below the table is the unsimplified Boolean equation for the left back signal light.
The easiest way to simplify the Boolean equation is to use a K-map. Here's a K-map for the left rear signal light. In green, we see that the S and R terms change while the C and L terms do not. Thus, we have C and L. In red, the L and C terms change while the R and S terms do not. Thus, we have R and S. And in blue, the R and C terms change and the S and L naught do not. Thus, we have S and L naught. ORing these terms together, we get C and L, or R and S, or S and L naught. Using the same technique, we can simplify the Boolean equations for each of the signal lights. The results are shown in the table below. Here's an implementation of all of the signal marker Boolean equations into one circuit. Since the C and L term is used in both the left front and left rear signal, we can use the same AND gate to, if you will, AND the C and L together for both signals. This reuse helps reduce the number of gates required. The same is also true of the C and R term. Notice that this circuit uses a total of 2 NOT gates, 6 2-input AND gates, and 2 3-input OR gates. Here's an implementation of these same equations using a ROM instead of the gate. Notice we now have just one component on our board. Now, while that ROM looks neat on a diagram, it must be programmed to function properly. Here's the truth table again. Notice that the inputs and outputs have been translated to hexadecimal numbers. For now, let us look at input row 8. Notice that the output of the various signals has been converted to a hexadecimal value of 5. To program a ROM, we insert the hexadecimal value of a row into that position in memory. In our example, we would program a hexadecimal 5 into the 8th position of the memory. Now, when input 3 is high, input 2 is low, input 1 is low, and input 0 is low, this would represent a value of 1000 in binary, or 8 in hexadecimal. This would trigger the ROM to output the value within the 8th position of the memory. Since it had been programmed with the value of 5, the ROM would output 0101, which is the binary equivalent to 5. This would mean that the third output would be low, the second output would be high, the first output would be low, and the 0th output would be high. And this would be repeated for each row of the truth table. Now we can test the circuit.
Here we see that the inputs of R and S do in fact cause the left back signal output to be high. Same output with the ROM. Here we test the CL inputs on the gates and see that the CL inputs do cause the left back signal output to be high. This also causes the left front output to be high as expected. And we see the same output with the ROM. Here we test the SL not inputs on the gates and see that the SL not inputs do cause the left back signal to be high. This also causes the right rear output to be high as expected. Again, we see the same output with the ROM. As demonstrated, using gates or ROM can deliver the same results. Either technology could be used to create a vehicle signal control circuit. While the vehicle signal control circuit could be created using either gates or ROM, using a ROM will reduce the number of components needed. Each may reduce the cost and increase the speed of the circuit. Thank you for your time. We hope you enjoyed the presentation of the Road Ripper Lab.